Okay, here we are. So I'll usually, if I'm doing, instead of cleaning up the bench, I usually use new bench. So just take new workbench. Okay. We require 150 ml burette. We require a beaker. We require strong. Usually the titrations are done in alumni flask, yeah, not in beaker, but we'll use beaker for the titration. And where is it? 10 molar. Yeah, that's 10 molar H2SO4. Close the shelf. We take indicator, it's already open, and take strong base, which is 3 molar NaOH. Okay. Alright, in the beaker we transfer 25 ml of H2SO4. We did. Okay. We add, you can check if it is 25 milliliter, you can check the pH. Yeah, it's -1 right here. Yeah. We add 0.25 milliliter of phenolphthalein indicator. It's gone. And now, yeah, we talked about this. It's about hydrogen ion concentration. Yeah, so it can be negative in some cases. It's about just how much of hydrogen ions are there. pH is not pH is an indicator of how much of hydrogen ion concentration is in there. So the dissociation of H plus is didn't you attended our class on acid base chemistry? Yeah, 1 to 14, but I also explained to you that it could go negative in some cases. No, there is. I mean, there is definitely an extent. It can. The reason is if the more after this point at from from 0. So from 1 to 14 is the standard range. It's a logarithmic scale, correct? After 14 and before 0 or below 0, the scale does not actually work in the same way because it is a logarithmic scale. Yeah, it does not. So you'll have to produce more and more OH ions to see, or you'll have to produce more H plus ions to see even a slight change. Okay, so it's about the dissociation of acid in the solution and how much of, so for every 10 H plus ion you will see of or 10 degree increase in H plus ion, you will see a 1 degree change in pH. So obviously after some extent those H plus ions becomes difficult to produce, and so but it can go, I don't know how negative it can go, but after -1 or so it becomes increasingly difficult to push the pH even more down. Same case with above 14 pH, but it can go above 14, it can go below 1 to some extent. Yeah, not a lot. Alright, so let's talk about, and so you can see it clearly from here, it's just the H plus ion concentration. So you can see that H plus ion concentration has increased a lot. How much was it when you had it H plus when you had HCl, 1 molar HCl 25 milliliter? Let's see, let's talk acid. You had, where is it? I always don't see it. It's weak acid. Oops, we need strong acid. Yeah, so let's see that H plus ion concentration. 1. Yeah, H plus ion concentration is 1, whereas in H2SO not here. Yeah, here you see that it is 9. Yeah, so it's actually 9.9, so it's almost 10 times more H plus ion concentration in there as that of HCl. And so for 10 times more you see 1 degree lower in pH. Yeah, obviously there is an extent to how much H plus ion you can dissociate, and so yeah, there are also super acids which dissociates very rapidly. Yeah, and those will probably have slightly lower pH, probably minus 1.5 or maybe minus 2 or something, but um, not a whole lot lower. Okay, let's add 50 milliliter of NaOH in there. Yeah, so we add 50 NaOH, remove that. We needed to add, so we haven't added, we did. Yeah, so we have phenolphthalein indicator in there. Okay, now we do the titration. Yeah, everything is in place. We have 25 milliliter of HCl, 0.25 milliliter of phenolphthalein indicator in the beaker. Start adding 0.5 milliliter of NaOH into the beaker each time you click enter. Yeah, and so you can see the pH is going up with each addition, and so it was like 15 milliliter, right? We calculated would require 15 milliliter of HCl, so the total volume should be 40. At 40 we should see neutralization. Is it? I think I did something wrong. Yeah, I think we took 1 molar NaOH or 3 molar NaOH. Yeah, I think we messed up on the NaOH. Yeah, we took the wrong NaOH. Yeah, I think so. Alright, let's restart. Take new workbench. 50 ml burette. It's easy to work on virtual labs because I don't have to clean. Otherwise cleaning is a mess in chemistry. You have to do a lot of cleaning, man, and you have to clean like nasty chemicals. So take 10 molar NaOH, you take H2SO4, 10 molar, 3 molar H2SO4, is it? Yeah, so that's 3 molar H2SO4, and we need indicator, which is phenolphthalein. Okay, now I think, yeah, we did the wrong chemicals. So we take 25 ml of that, add 0.25. So I think, yeah, for this one I think this one the pH is probably slightly negative. Yeah, it's not as much. Yeah, so we have the right volume. Now let's add NaOH into the burette. We get 50 milliliter of NaOH. Fill it up. We don't have to worry about wasting virtual things. Alright, now just keep adding 0.5 each time we are adding NaOH. You can see the pH is going up. Yeah, this is going to work. I can see it. You can see the concentrations are now coming down fast. Yeah, 36, 37, 38, 39, and now it should be bingo. You can see that the pH is slightly above 7 actually, but it's almost, yeah, it's below 8. Yes, it's 2,5 is the phenolphthalein, correct? So that also actually adds to the pH of the solution. so it makes it slightly acidic actually, the pH. So as a result you require that much extra of base. Okay. So now the pH, so this is the neutralization point according to us. The pH is again an indication of H plus and OH minus ion dissociation. Yeah. But the solution could be neutral. The temperature is probably very high at that point. Yeah, so now you can see that the temperature is going down. You can see that during the process the temperature goes up significantly in this particular lab. Even when you do HCl and NaOH, if you touch the flask the temperature is higher. Yeah, so it takes a little bit time to cool it down. Some of the titrations you actually need to do in ice, yeah, to keep the temperature low, because that actually shifts the equilibrium point. Yeah, we talked about this. So now the addition of 0.5 should give us, now at this point the solution is alkaline, but we don't see the color change because that is not the range where phenolphthalein changes its color. Okay, you can actually see the phenolphthalein indicator here. Yeah, this H plus or phenolphthalein H has higher concentration. Phenolphthalein H minus or phenolphthalein minus actually has a lower concentration. Yeah, you see that? As a result of that there is no color change, and the phenolphthalein would change color I think at around pH 10 or probably around 9. Okay, because this hydrogen needs to be removed, and that, so here in this case phenolphthalein itself is acting as an acid. Yeah, and the OH minus ion now is going to take out this hydrogen and convert it into a base, phenolphthalein ion. Okay, and so if you have more concentration of phenolphthalein ion, the solution is going to be pink, because this particular species is actually pink. Okay, the above is colorless, the below is pink. Understood? Okay, and there you go, and you can see that now the phenolphthalein is actually more, phenolphthalein ion is more, phenolphthalein is less, and as a result you see a pink. So if you have maybe if you add a little bit more, I think OH minus ion, it should the equilibrium should turn to right. Yeah, and you should get more of phenolphthalein ion, and so the solution should turn even more pink. Yeah, but this is the end point, and so we calculated, according to our calculation we needed to add a little bit more of acid. Yeah, we added I think 0.5 ml of extra acid, extra base in there, and that's again because of the phenolphthalein. Okay, so you have seen here that it took us 15 milliliter of NaOH to neutralize 25 ml of 3 molar H2SO4 solution. Yes, so that is the titration. Yeah, so it proves basically, so you can use mole concept, you can use equivalent concept, or you can use an actual experiment to come to the same conclusions. Any question on this one? Okay.